Welcome back. Now that we understand the basic density functional approximation DFT density functional theory as we said, which is rather a difficult concept. So, I want you to take your time to understand that, and that is where we are making certain approximation. However, we are keeping the electronic structure intact and we are going to use quantum mechanical formulation here, and that was the ingenuity of Carr and Parrinnello. They said, how can we come up with a method for molecular dynamics simulation potential function where we can keep the electronic structure. And some of these Car-Parrinnello method, when it is used for system of metals or system which are where we have to consider the electronic structure, they work extremely well. And so, I think while we have some more complications in terms of the formulation, but we are gaining a lot in terms of the accuracy. So, let us move forward and let us begin by writing some equations here about different parts of the Car-Parrinnello method, which is called unified approach for molecular dynamics and density functional theory. The reason it is called unified method because it is now going into electronic state. So, now any atom can be handled by it. However, more complicated the atom is, more complicated their atomic mass number is, there are more shells, there are more things to fill up. So, if you go from hydrogen atom to let us say uranium atom, you can use some of these approximation. However, it becomes more and more difficult in order to keep track of it. However, these approximations work very well. So, one begins with the writing energy of the system of ions and electrons. So, if you look at, we are looking at the charge densities here, that is where ionic interaction comes into play. So, every atom has hydrogen. Let us say look at the hydrogen atom, you have nucleus where it has proton and neutrons, and then you have electrons. Electrons are the shells around it. Now, if you look at, if you have to make that, so postulate, so you have positive ion or positive electrical charge on the protons and the negative charge into electrons. So, now we are interacting between protons and electrons, and of course, the neutrons are neutral. So, that is where they are not participating in this, but if you look at ionic positions and you are looking at electrons as a wave function. So, we look at the positive charge, the nucleus, and that is where Born-Oppenheimer approximation is still valid. So, now what we are going to do, we will look at the energy function E in terms of psi, which is the wave function, and R is the position. So, we are looking at the position and the wave function instead of position and velocities that we looked at in Newtonian models. Now, in this case, we are going to look at positions and the wave functions. So, if you look at the position and the wave function here, it is a triple integral. If you look at 3-dimensional integral, and it is a discrete. So, you are going for each ions from I to n, whatever the number of ions are in the system. The first part is wave function. So, if you look at this part is the quantum mechanical, the other part is the potential energy function u, and that u is calculated from the positions of the atoms. Now, if you look at this expression gives the Born-Oppenheimer energy when it is minimized with respect to r. So, now we are looking at with respect to r. To do this, one have to solve the Kohn and Sham equation, and which essentially gives you a equation that allows you to optimize the location of r. As you know from our previous approximation, which says that the ground state energy is function of rho r, which is minimized when rho r is the correct charge density. So, this is where Kohn and Sham equation is used, and you know Kohn-Sham equation allows you to go into the single particle model, and that single particle equation now, which is an approximation, now can be minimized for the r. So, if you look at since this is a homogeneous equation, it is typically solved by expanding in a set of basis states, often chosen to be plane waves. So, you can take bunch of plane waves and solve this equation, minimize it, and then diagonalize the resulting matrix, which is a typical way you would solve this kind of equation, which is second order Nabla square delta u over delta n r, which is all the number of particles here with respect to r. We are looking at the basis vector. However, at this point Carr and Parrinnello proposed a different approach by regarding the minimization problem as a complex optimization that can be solved by applying the technique of simulated annealing. So, we said and this is where sort of connected with our idea about minimization using simulated annealing. And as you understand from Monte Carlo simulation, where you can find simulated annealing and create these random locations to sample this potential energy minimum surface. So, instead of doing this complicated calculations, what Car-Parrinnello came with the idea that why don't we use simulated annealing utilizing Monte Carlo method or any other method of minimization, which will quickly get us to the minimum solution of the equation rather than complex optimization where you have this n body problem. So, this is where they had some idea which was very useful. With that minimization, now you can look at the equation of motion to some extent. We are not looking now into Newtonian, but we are looking at Lagrangian, and that Lagrangian is also quantum mechanical Lagrangian, unlike the Newton's law of motion that we looked at earlier, and we were able to use Lagrangian in order to calculate the temperature, and we utilized in canonical ensemble. However, in this case, now in Car-Parrinnello Lagrangian, what they introduced, they essentially had three terms here. One was the wave function term, and the other one was the term for all mass as well as the position of the atoms. So, the position vector, the wave vector, and then the energy. Now, you remember from the previous equation we could calculate energy using wave function and the location of the ions, and that was calculated using this quantum mechanical equation. So, if you plug that E from the previous equations, now you have a full definition of the dynamics in respect to this density functional approximation. So, now we have a handle to and now we can take this particular factor, which is Car-Parrinnello equation, and apply the Lagrangian dynamics to this particular factor. And if you look at d delta nabla over dq, and so if you look at this, this is the same format as the Lagrangian equation for the Newtonian side. So, all we are changing is we are changing this with a quantum mechanical factor, which we calculated with 3 items in it. With that equal to 0, now we can use the Car-Parrinnello method to calculate different quantities, where we can now find the idea electron and ion masses. So, we have mu as the electron mass, and if you look at these ion masses are included in order to find now the kinetic energy, because mass multiplied by velocity square mv square by 2 was the Newtonian model. Now, we are going away from Newtonian and we are into quantum mechanical. So, in this case, if you find out the kinetic energy, then you have one is the wave coming out of the wave vector, and you have mu psi double dot here, which is giving you the second order differential like acceleration in the wave form, and then it is also giving acceleration with the mass multiplied by the distance square, which is this is more Newtonian type, which is equivalent to what the energy changes are happening on the other hand. So, now in this equation we can regard the kinetic energy, we can add these terms. So, 1/2 of all 3 dimensions of wave vector square over mr. So, this is the formulation now for the kinetic energy, which is now becomes the basis for your calculations in the quantum mechanical way using Car-Parrinnello's density functional approximation. So, if you look at as a kinetic energy E and E as the potential energy. So, you have kinetic energy and you have E, which is the potential energy, which we calculated earlier. We note that now we have both potential energy and kinetic energy. By associating average value of k with a temperature T, we can minimize E by reducing T gradually to 0. by variation of the velocities of the wave vectors and r, which is the position vector. At equilibrium t is equal to 0, obviously the wave equation second order will be 0. Then if you look at this equation above and minimize it to unitary transformation, that is when you can come to the ground state, and that is where you are now able to use the density functional approximation. So, in this approach, diagonalization, self consistency, ionic relaxation, volume and strain relaxations are achieved simultaneously, because we are using simulated annealing, and that model allows us to simultaneously change all these parameters. So, you increase the value of all the parameters, bring them down very quickly, and that is what we call is a Car-Parrinnello method, and that is the first principle method. There are some issues with that. So, let me go through very quickly, which is DFT, density functional approximation, and local density approximation is very successful in describing static lattice constant less than 1%, and dynamic properties of the solid. That is a good part about that. So, metal, insulator, semiconductors, we can handle that using Car-Parrinnello method. Approach has difficulty in describing excitation energies of quasi particle band gaps of semiconductors and insulator. So, there are some more additions you have to do if you really want to get into semiconductors using this kind of approach. Method is computationally intensive. So, N 300 and time step smaller by a factor of almost 10 times less smaller. Let us say if you do picosecond, you have to go 1/10 of the picosecond, and the number of atoms that you can use is not a large atom, although with today's computation power you can do a lot more. But what you get, the results are very good and accurate. Lattice constant, for example, is accurate within less than 1%. Bulk modulus is within 5% of the accuracy, which is phenomenal. If you look at phonon frequencies, is also close to 5% accuracy, and then you can also calculate diffusion constant and other with much better accuracy than any other method. So, let me stop here. This really gives you a very broad understanding of Car-Parrinnello method based on the first principles and density functional approximation. Thank you.